The next additive manufacturing process that we're going to look at is powder bed fusion. Powder bed fusion is part of the powder-based categories for additive manufacturing process classifications. Remember that this is the standardized classification system that is being used by the ISO and ASTM right now. So powder-based processes include binder jetting, powder bed fusion, and directed energy deposition in its powder form. Powder bed fusion began in the 1980s with Carl Deckard while he was a professor at the University of Texas in Austin, and he developed a process called selective laser sintering. Okay. In 1987, Deckard co-founds Desktop Manufacturing, DTM. And a few years later, DTM commercializes the first powder bed fusion process known as selective laser sintering. 2 years later, EOS, a German company, commercializes EOSint, EOSint, machine-based laser sintering. In 2001, 3D Systems acquires DTM and the SLS technology. And also in 2001, Concept Laser, which is a German company, develops a new system that combines laser sintering, laser marking, and laser machining. And in 2002, Arcam, a Swedish company, launches the first production EBM machine. EBM stands for electron beam melting. All right. So there's a lot going on here. You can see that it started with selective laser sintering, which was a plastic process, a polymer powder-based process. And then it develops from that into essentially a metal-based process. Of course, metal powders and metal plastics are similar in a lot of ways, dissimilar in a lot of ways too, but similar in a lot of ways. And that allowed powder bed fusion to kind of expand and become the first developed 3D printing process that used metal, or that could use metal. The basics of the powder bed fusion system work like this. Okay, so first, what is the official standard definition of powder bed fusion? It is an additive manufacturing process in which thermal energy selectively fuses regions of a powder bed. Right? So understand that nowhere in there does it define it as a plastic or a metal process, right? So it basically says that you're going to use heat, thermal energy, to fuse regions, different areas, specific areas of a powder bed. All right. So the build material in this case could be many things, anything that you have in powder form. So that could be polymers, plastics, metals, ceramics. The material distribution method is going to be from a bed, right? And that is assisted through either a roller application or a blade application. And we'll look at how that works in a few slides. And then the binding technique, as you can see from the definition, is thermal energy. And that usually comes in the form of a laser or in some cases an electron beam. Okay. So in the process over here, if we look at the figure, you can see the laser is going to be using another galvanometer, right? So that this is going to direct the laser beam on into a specific kind of outline for each layer, right? And it's going to hit specific areas on the powder bed. So this area right here is the powder bed. So the laser is going to be directed onto specific areas of the powder bed to fuse those layers through the application of this thermal energy, the heat. Okay. This whole area here is going to be ultimately filled with powder, right? And so there's no need for support material. This is one of the advantages of powder bed fusion, is that the part that you're 3D printing is going to be surrounded by the unfused powder. And so therefore there's no need for any support structures. The support structure is the unfused powder. All right, so let's move on to a little bit more of a specific look at the process. Okay, so before we get into the basic outline here, let's look at the figure. All right, so you can see there's 3 areas where we have powder. All right, so the powder is going to start in this left powder feed supply. So imagine that this powder is filled, or this area is filled, this reservoir, and the powder feed piston in this case is going to be as low as it can go, right? So this area is filled with powder. In the middle area is where the 3D printing is going to occur. And here the build piston is going to be at the top level, okay, of the chamber. And actually, as the part is being made, or at the point of time that the initial layer is going to be formed, the build piston will move down 1 layer thickness. Okay, so whatever that is, 1 layer thickness, the build platform is going to move down. And at that point, a roller or a blade is going to take the powder from the powder feed supply, and it's going to roll or distribute it across the entire surface of the build platform, right? So remember, the build platform has moved down slightly, 1 layer in height. So this roller is going to roll across, and it's going to distribute the powder and fill that whole area in the build chamber. All right. Then the laser is going to fire, and it's going to fuse all the powder in the specific layer that you're building. And then the whole process is going to start over again. The build piston is going to move down. The leveler, or the blade, or the roller, whichever one it is going to distribute another layer of powder across now, and so on and so forth. So let's look at the basic process here. Step number 1, a layer of material is spread over the build platform. All right. Step number 2, a laser fuses the first layer of the model. 3, a new layer of powder is spread across the previous layer using the roller. 4, further layers are fused and added. 5, the process repeats until the entire model is created. Loose, unfused powder remains in position as support, but is removed during post-processing. All right. All right. So, what are some important powder bed fusion technologies and companies that are developing this kind of additive manufacturing process? So, we have selective laser sintering. Or actually, let me back up a little bit. The powder bed fusion process is known for its, among other things, its crazy amount of acronyms and abbreviations for the processes. Okay, so you'll see printing, melting, and sintering. All right, and in addition to cusing, laser cusing. So we have selective laser sintering and laser sintering. And that material is polyamides, which is plastics. Okay. And the major industrial manufacturers are the EOS system and 3D systems. Then we have direct metal laser sintering, right? So the metal in that kind of gives it away. These are all going to deal with metal, and that's EOS. Direct metal printing, 3D systems. Selective laser melting, all right, again, by a metal by SLM Solutions, which is a German company, or Renishaw, which is a British company. Laser cusing, which is from a company called Concept Laser. And then EBM, electron beam melting, which is the Swedish company Arcam. All right. So in a broad kind of sense, if you see the word sintering, it typically applies to polymers or plastics. Okay. If you see the word melting, it typically applies to metals. All right. That doesn't mean that there's much difference going on. It just means that that's how they've differentiated the two. Of course, the one outlier is direct metal laser sintering, which is a metal process, but it uses the term sintering. All right. So, let's move on to the basic characteristics of powder bed fusion. Okay. So what basically do all these processes have in common? So we have one or more thermal sources to induce fusion between the powder particles, and that can be either a focused laser or an electron beam. We have a method to control the fusion to the prescribed region on each layer, right? So that means we need to direct that laser into the specific outline of the part on that layer. Okay. And that's done with a galvanometer in the same way that the laser is controlled with the vat photopolymerization process when you're using the vector scanning technology. Okay. Remember, a galvanometer is basically a servo controlled mirror that's going to be moving in such a way that it can direct the laser. And then we also need a mechanism for adding and smoothing the powder. And that's either going to be a roller or what's called a doctor blade. And the doctor blade is just a fancy word for a squeegee. Except in this case, you know, you're used to using a squeegee to like remove water from your windshield. In this case, we don't want to remove the powder. We basically want to scrape it across the surface and distribute the powder evenly. Okay. And then, as I said, powder bed fusion was originally developed for plastics. Okay. All right. So what are some of the strengths and weaknesses in the powder bed fusion process? Well, the strengths are it's relatively inexpensive. It's suitable for visual models and prototypes. The powder access support, that's a big plus. You have a large range of materials. Basically anything that's in a powder form, you can use it this way. So there's a lot of metals that are able to be used here, in addition to different plastics, polymers. The parts can be stacked. We'll talk about that. But because we're printing in basically a reservoir of loose powder, right? Whether it's metal or plastic, we can stack parts on top of each other, all right? Because we have an inherent support structure in there. And then we can recycle the materials. Not an infinite number of times, but all the unformed powders, whether it's plastic or metal, can be reused a certain number of times. There is a limit to that because the reservoirs that we're dealing with, the reservoir, certainly the reservoir that the part is being built in, is being heated, right? So it's at an elevated temperature. So even though the loose powder around the part is not at a sintering or a melting temperature, it still is at a high enough temperature where it's going to degrade the material. And so maybe you have 2 or 3 applications of that powder before you need to get rid of that powder and get new powder in there. Some of the weaknesses are you need a completely controlled environment. Okay, so that means you have the build area. The entire machine needs to be controlled. So the build area, the reservoir is going to be heated, and you also will need to heat the supply of powder, whether it's plastic or metal. That area needs to be heated, so there's not a large temperature difference between the supply and the reservoir with a building. But you also have powder particles, right? So whether it's plastic or metal, powder particles are very dangerous, right? They can be explosive. They're very bad to inhale. And so the whole build area, right, is going to have to be controlled. The powder reservoirs and supplies are also controlled environments. So that means that the machines have to be of a special they have to be specially made, purpose-built for this. It's typically a very slow speed process, right? It takes a long time to heat up the reservoir and the supply. It takes a long time for it to cool down, especially in the case of metals. This can take hours, okay, or in some cases days. You do have size limitations, right? So the reservoir where you're building, the build reservoir, is not so large. Typically, it's on the order of, and we'll see some actual numbers here, but typically it's on the order of a 6x6 or 8x8 square at its largest. And then it also uses high power. All right. So this is there's a lot of heat that you have to apply. The lasers are very powerful, especially in the case of the metal. And so these are all the weaknesses. And that's why you're really not going to see this for home use, especially the metal processes. The machines tend to be very expensive, upwards of $250,000 or $500,000 for different types of machines and what they do. So let's look at the powder bed fusion materials, right? So in the powder bed fusion process, material in powdered form is melted together using a thermal energy source, right? Typically a laser. So the build material in this case can be thermoplastics, metals, ceramics, or even composites. The thermoplastics are ideal for powder bed fusion, right? Because they have a low melting temperature. So that means we don't have to apply a lot of thermal energy. They have low thermal conductivities, and what that means is if we have an area of powder that we're melting together, for want of a different term, an area of the powder that we're melting together, the surrounding areas of the powder are not going to be so affected by the heat. So in other words, the powdered plastic has very good insulative capabilities, and so we don't have heat being transferred throughout the whole reservoir, which would be very bad. Okay, it has a low tendency for what's called balling, or this is a tough word to say, spheroidization of the liquid melt pool. All right, so let's back that up and kind of try to figure out what that means. The liquid melt pool is basically the specific area where the laser is melting the plastic, or the powders, right? So think of that as like a little melt pool, right? A puddle, right? And so what we don't want is we don't want this clumping effect where we get a balling of the powders that start to lose all of their dimensional integrity, right? Or so they start to clump, right? We want, in the powder bed fusion process, in addition to the other 3D printing processes, but specifically in the powder bed fusion process, we only want to melt specific areas of the powder. We don't want that heat to transfer out, and we don't want powders to kind of glom onto each other and make clumps, right? And then it also has limited recycling due to the sintering of loose powder over time, as I talked about in the last slide. So there's two types of thermoplastics that are used in powder bed fusion. We have semi-crystalline and we have amorphous. All right, we talked about this a little bit in the vat photopolymerization lecture, but the semi-crystalline looks like this on the far right hand side, and you can think of these as more or less orderly strands of polymers, right? So you can see it kind of looks like it's like there's just rows. You see it gets a little bit wild here in the middle and on the ends and whatever, but nothing like the amorphous thermoplastics. So the amorphous thermoplastics, remember I said that it's kind of like we take cooked spaghetti and we drop it on the floor, right? So we're not going to expect that spaghetti, those strands, right, these polymer strands right here are going to be organized. So they're just going to be randomly falling down. This is a random molecular structure. The polymer chains tend to be intertwined. They soften and melt. So the amorphous thermoplastics soften and melt at a wide range of temperatures, which you might think is good, but actually it's not good, right? We want, in the powder bed fusion process with polymers, we want a defined, easily known and attainable melting temperature and even softening temperature, right? So we don't want a wide range of that, because that's going to mean that we are going to have trouble getting the part either to melt, or the areas to melt, or they're going to melt too much. All right. So the semi-crystalline actually is a better a better thermoplastic for the powder bed fusion process, because it has a distinct melting temperature. So some of the thermoplastics that we use in the powder bed fusion process include polyamides, which the normal word for that is nylon, or the common term for that is nylons. This is the most common polymer for powder bed fusion. It has a semi-crystalline structure. So remember, semi-crystalline means it has a distinct melting temperature. It's very repeatable processing. Right? That distinct temperature really helps in that. Okay. It cools quickly and uniformly, and it has a high density, right? So that means it's not porous. It's not going to absorb water or moisture, and it's going to behave, quite predictably. Now, looking at the metal characteristics, right? There's a wide range of metals available. Any metal that can be welded, can be made into a powder and used in the powder bed fusion process. And that's a wide range. So that includes stainless steel, tool steel, cobalt chrome, titanium, aluminum, Inconel, which is nickel, and other nickel alloys. This also includes gold and silver, right? Precious metals. Thermo-coated, binder-coated metals, right? So that means that we have metal powder that has a plastic coating on it can also be used, right? So those are polymer-coated metal powders. Powder and ceramic and composite characteristics include metal oxides, carbides, and nitrides, and composites such as Cermet, which is a metal ceramic composite, and other glass reinforced polymers. So, they're compared to material extrusion, which has, until recently, there was no metal that you could print with that. And now we have, of course, with Desktop Metal and Mark Forge, they have their metal 3D printing. But, we have the thermoplastics. And then with that photopolymerization, we have the thermosets. But now with powder bed fusion, we have kind of all of that. We have the thermoplastics, and we also have a wide, enormous range of metals, plus these very excellent compounds, ceramics that are used in tooling to make very strong parts, very heat resistant parts. And so there's a lot of interest in powder bed fusion because of this wide range of materials. I should also note that all of these materials in their powder form, the powder thermoplastics and the powder metal, this is not new technology, using these as powder. Powder metallurgy has been using metal powders and to some extent plastic powders for ages and ages, decades. And so the powder is there. So it's not really a process of making the powder. The powder is already there, and this is just a new application for utilizing that powder in an innovative way. All right, so I think this is a good place to take a break. When we come back, we'll talk about powder fusion mechanisms, or the mechanisms that are used to fuse the powder, metal, and polymer together.